Okay, so in this first unit, the two graphs that are going to be most important to us are position versus time graphs and velocity versus time graphs, which, as I just finished saying, you've already covered in Science 10, and I'm really not going to teach you anything differently. It's basically just a review, okay? That these are how these graphs work, what you can read from these graphs, how you calculate this from this graph, okay? Stuff like that, and some graphing basics, right, is all we're going to cover here today. Right? So what we need to get out of today, understand what information can be read from these kinematics graphs, understand the graphs and equations from your formula sheet, okay, are actually derived from graphs, okay, and they just express the information in different ways, right? So that's what we're going to be looking at. The other thing we're going to look at, okay, and hopefully this will be a review for you as well, okay, is the importance of this. Okay, how many people did that in Math 10? Okay, good. Right. Y equals mx plus b is the graphing equation for a linear relationship on a graph. Okay, it's pretty straightforward, it's easy to use. Okay, we're going to look at how it applies to a position versus time graph and how it applies to a velocity versus time. All right, in Science 10 when you learn this graphing stuff, you may have just memorized. Okay, well on a position versus time graph, this represents this. Velocity versus time graph, it represents this. Okay, and while that'll get you through Science 10, it's gonna catch up with you if what you do with every graph is memorize everything for every graph. Okay, in Physics 20, we'll have about a dozen different types of graphs that we'll go over. You get to Physics 30, and that number doubles at least. Okay, so being able to memorize what everything on every graph you use is going to become confusing and cumbersome, okay? So what we want to look at is how can I just interpret any graph and get what I need from it, okay? It's better to have a skill that can be applied to any graph than to have to memorize every graph. So that's what we'll look at a bit here as well, okay? And that's where, again, the importance of this is going to come into play. This applies to every linear graph, so we'll use it that way. All right, so for a position versus time graph, one of the things you're going to be expected to do is be able to look at a position time graph and interpret from its shape what is happening on that graph, and basically from any graph, okay? What is going on that graph? So a position versus time graph tells us where the object is at various points in time. That's what can be read directly off the graph, okay? So if I'm looking at this graph here, at the beginning of this graph, I have a line that's straight, diagonal, but straight. Okay? And it says here that that part of the graph represents the object traveling at a uniform velocity of 180 kilometers per hour. How do I know on this graph that a straight line represents a constant velocity? The speed isn't changing. Okay, again, how do I know that that's what this diagonal line represents? You're right, it means that it's not changing, but how do I know that? How can I interpret that?
That distance is changing at a constant rate.
What's on the y-axis, position or distance, is changing at a constant rate. Okay? Now that can be applied to any graph. What's on the y is changing at a constant rate if the line is straight. Okay? A linear relation, there's a constant change in y over a constant change in x. Okay? What I have to look at is, what does that mean for this graph? Well, on this graph, position is the y and time is the x. And I have a formula that relates those two things. Change in position divided by time calculates what? Velocity. Okay, so if I have a relationship on this graph where the position is changing over time, I have something traveling at a constant velocity. Okay, I just interpret from the graph what's going on rather than memorizing that if I have a straight diagonal line on a position versus time graph, that means, okay, rather than memorize, I just interpret from the graph. Okay, now, after this point right here, okay, we see that the line starts to curve. Okay, and as it curves, it's flattening. Okay, if it's flattening, what's happening to how quickly I change my position? let me ask that a different way, because now that I hear that in my head, it sounds confusing. What's the object doing here where the line is flat?
Stopping.
It's stopped, okay? Because if the line's flat, the position, which is on the y-axis, is no longer changing. So if I go from a line that's diagonal to a line that is now flattening, that means that it's going slower and slower. Okay? The steeper the line, the faster it goes, because the steeper the line, the more the position changes over time. If the line's getting flatter and flatter, that means it's going slower and slower. Okay? So again, it's not a matter of me memorizing that, it's a matter of me looking at the graph and going, okay, it's not changing as quickly anymore. On this graph, position's not changing as quickly over time, that means slower, or slowing down. Okay? I just interpret to each graph. All right, so here we have a deceleration or a negative acceleration. The object's going slower and slower and slower, which is why the line is getting flatter and flatter and flatter. Okay, and then when we get here, okay, to here, the object is stopped because there's no longer any change in position. There's no change in position, you're not moving. After this point, we see that the line is starting to get what? Faster, right. It's curving upwards, which means the line or the curve is getting steeper and steeper and steeper. The only reason it gets steeper is if the amount we change our position by is getting greater and greater. In other words, we're going faster and faster and faster. Okay, so you're accelerating during that curved part. Okay, then we get to here and the line becomes straight again. Okay, if it's straight, now it's changing its position at regular or constant or uniform rate. In other words, it's traveling at a constant velocity. It's no longer changing the steepness of the line. Now the steepness of the line is constant. Okay? That's the kind of thing we have to interpret from a graph. I could very easily put a quiz on a question or a test that says, here's a position time graph. Tell me what's happening in section A, B, and C. Okay? And you have to look at the graph and go, all right, here we've got something changing at a constant rate, the position's changing at a constant rate, that means constant velocity. Done. Okay? That's what you would have to do. Interpret the graph and tell me what's going on. Okay, everybody all right with that idea? Okay. Now, with slope calculations, you may have learned one or the other of these, or both. Okay? To calculate slope, sometimes you're told to do this. Slope equals rise over run. How many people have heard that before? Okay, that's perfectly fine. There's nothing wrong with that. It's right. Slope does equal rise over run. Okay, that means the change in y over the change in x, which is also sometimes written like this: y2 minus y1 over x2 minus x1. Okay, does that look familiar to some people? Okay, that's fine. That formula is true and it works. The problem with it is it only calculates slope. Okay, and that limits its usefulness to us. Okay, that's why in physics we prefer this. Which part of that formula represents slope? M. Okay, M represents slope. All right, if I want to solve for slope, what do I move first? I should move? Somebody said it, I thought. B, yeah. Okay, so first I'm going to subtract B. So I'm going to go y minus B equals m times x. I want to get m by itself. What do we do with x? Divide it over, right? Okay, so now I've done that. I have y minus b over x. Well, if I'm looking at a graph, okay, this is like y2, okay? This is like y1, right? Well, this can also be y, and this is b, right? This change here is x. Is that the same formula? Okay, this is the change in y. It's y2 minus y1 divided by the change in x. Okay, it's exactly the same formula. The difference is y equals mx plus b can be manipulated to find a y value or an x value, okay? And it's more useful that way. Right? So that's where this formula here, that comes from that formula. Okay? That's how we calculate slope. Okay? B is the y-intercept. It's where your line crosses the y-axis. It's essentially what is y when x is 0, or at the beginning of the experiment. All right, everybody all right with that? Ringing a bell? Okay, so here's a position versus time graph. What is the object doing in part A? No. Okay, in the first 2 seconds in part A, the object goes 2 meters. Okay? After 4 seconds, it's gone 4 meters. Okay? After 6 seconds, sorry, did that wrong. Let me do that again. Okay, so this thing here, it's showing its diagonal line, right? Is it going up at a constant rate? The position is changing at a constant rate. What does that mean? Starts with V. The velocity is constant. Okay? But right away, as soon as we see that line going up, our brains automatically go to changing, changing, changing. It's accelerating. But it's not. The rate at which it's changing position is changing. Or sorry, the position is changing, but it's changing at a constant rate. If it was changing at a non-constant rate, then it would be accelerating. Okay? But in this case, it's changing its position by the same amount every second. Okay? So it's moving at a constant velocity. All right? What is that velocity? I don't think 2 meters per second. Okay? What's my initial position at the start of A? 0. Okay? What's my final position at the end of A? 6. Okay. Velocity is the change in position divided by the change in time. Everyone okay with that? Okay. We just said my final position was 6, my initial position was 0, and that took 2 seconds. 6 over 2 is? 3. Right? Did I just use V equals V over T on a graph? Is it okay to do that? Absolutely. Okay. I don't know how else I would have figured out what the velocity was in part A. Okay? But I knew what the displacement was, I knew what the time was, I could calculate it using that formula. Okay. All right, what's the object doing in part B? It stopped. Okay, how do I know it stopped? Well, at the beginning of part B, it's at a position of positive 6 meters. At the end of part B, it's still at a position of positive 6 meters, which means it hasn't gone anywhere. So it must be stopped. Okay? Again, it's not a matter of me memorizing that a flat line means the object's not moving. I'm just interpreting the graph. Okay? The position didn't change during that interval, so it must have been standing still. Okay. All right, what's going on in part C?
It's going in a different direction.
Yeah, it's going in the opposite direction. Okay? Now its position is changing from 6, positive 6, to negative 10. Okay? It must be moving backwards. Is it accelerating backwards or moving backwards at a constant velocity? Moving at a constant velocity. Okay? We're seeing a uniform change in position. Okay? If it was accelerating, what would it look like? It'd be a curve. Okay? All right. Can I calculate the velocity during part C? I can. In the same way I calculated it in part A. Right? So for part C, okay, so the velocity in part C, final position, negative 10, minus the initial position, positive 6, and that took 4 seconds, right? Went from 6 to 10 seconds. All right, so I've got negative 16 over 4, okay, so negative 4 meters per second. Right? The math says that it was moving backwards, okay? Because I got a negative velocity. What's going on in part D? It's stopped. Yeah, the position is not changing during part D. It's stopped. It's at a position of negative 10 meters, okay, for another 2 seconds. Okay, where is the object going faster? E or F? E. How do I know it's going faster in E? The line is steeper. Okay? Steepness or slope, okay, tells us about how quickly y changes with respect to x. Okay? Since this line is steeper, the position is changing faster here than it is here. Okay? That means this is going faster than this is. Everybody all right with that? All right. I want you to answer a couple of things for me from this graph. I'm going to work them out on paper here. Okay? The first thing I want you to calculate is the total displacement over the entire trip. We should all be done now. It's 0. Okay? The total displacement over the whole trip is 0 because I started here at 0 and I ended at a position of 0. All right, the total displacement is 0. Now here comes the tricky one. What's the average velocity over the whole trip? 0. Okay, remember, velocity is change in position divided by time. What was our change in position? 0. All right, then our velocity's got to be 0 too. Okay, now you're actually going to have to do some calculating. I want the total distance traveled over the whole trip. Total distance. Remember, distance is scalar, so it doesn't care whether the object went forwards or backwards. Give you a few minutes on that. Was recording. We missed a bunch of stuff. Okay. Sorry, we're going to skip this part because it's not important. All right, so I've got this position versus time graph here. All right. On this position versus time graph, the object is doing what in every section? It's accelerating. In every section of this graph, the object is accelerating. Okay? And we know that because the slope of the line isn't a line. Okay? It's a curve. Now, I'm going to tell you the only thing I understood in university physics. Sorry, university calculus. Not even I understood everything in university physics. It was university calculus that really screwed me over. Okay? According to a mathematician, a curve is an infinitely large number of infinitely small straight lines strung together. Okay? In other words, when a mathematician looks at a curve, they see kind of what you see if you look at a low resolution picture or video online. If it's low resolution, what can you see? The pixels, the little squares, because that's how computers make things. Okay? The higher the resolution is, the smaller the pixels are, the harder they are to see. Okay? We can't see the pictures in a 4, or the pixels, sorry, in a 4K video because they're so small that we can't resolve them with our eyes, so it looks really sharp. Okay? But to a mathematician, a curve is made up of a whole bunch of little straight lines that just get steeper and steeper and steeper, or flatter and flatter and flatter, depending on which way the curve is going. Okay? So that means then that anywhere along that curve, there's a line with a slope that I can calculate. Agreed? Because these lines are constantly getting steeper and steeper and steeper, that means that obviously the object's velocity is changing. In this case, getting faster and faster. Right? So in this part, the object's accelerating in a positive direction, going faster and faster. What's the object doing here as it approaches B? Okay, well, let's have a look at it this way. Let's use this line to help us. Okay? So, down here, okay, the line points like this, right? Which is an object that's traveling forwards at a constant velocity, yes? Okay, if I move that line up here, okay, and I'm kind of following what B is doing, okay, the line is getting what? As I keep approaching the top of B, what's happening to the line? it's getting more and more what? Flat. Okay? Until when I'm finally right here at B, the line is flat, which means the object at point B at the very top of that little bell there, okay, the object is actually what? Stopped. Okay, and then if I continue to follow B, okay, and keep doing this, okay, I keep going past B, what's happening to the line again? It keeps getting steeper and steeper. So now it's actually accelerating in the other direction. Okay? You know what this is a graph of? This. It's a graph of somebody throwing an object up into the air. Okay? This part here is the part of the motion, okay, and actually up until right about here, okay, is the part of the motion where I am throwing the marker. Okay? I'm accelerating the marker upwards, making it go faster and faster and faster. Okay? The instant it leaves my hand, what's happening to it? It starts to decelerate. Okay? Because of what? Gravity. As soon as it leaves my hand, there's no force other than gravity acting on it anymore, and gravity is going to slow it down. Stupid gravity, always working against you and pulling you down. Okay? But that's what it's doing. Okay? It's pulling that marker down, slowing it down until, for an instant, the marker stops. And then begins to actually fall back to Earth. That's this part. Okay? So here's where the object is accelerating back towards Earth till about here, and then this is where I catch it. And as I catch it, I slow it down to a stop. Right? That line gets flatter down there. So we got to get to a point where we can look at a graph and really interpret what's going on. Okay? And be able to say, okay, this is an object that's doing this, and at this point in the graph, the object's doing this, and so on and so on. Okay? Would I give you a graph that was all curves? No. Okay? I might give you a graph that had one curve on it, okay? But I would expect that you'd be able to interpret what's happening just from the shape. All right. I want you guys to try this one. Okay? This is a graph of a bus. Okay? And it's doing this trip. Okay? I want you to find the average velocity of the bus during each interval. Okay? So this would be interval A, this would be interval B, this would be interval C. Maybe we need to make that bigger so you can actually read it. Maybe I can't. What's this? Hang on. This is in your notebook, your workbook package. All right, so if we want to find out the average velocities during each part and then over the whole trip, okay, we're using V equals d over t. Okay, or more specifically, we're actually doing this. Final position minus initial position over time for each section and over the whole trip. Okay, so for part A, we go from an initial position of 0 to a final position of 25. Okay, and that takes 1 hour. Okay, so over 1. So we got 25 kilometers divided by 1 hour, okay, is giving us our 25 kilometers per hour, okay? And that's positive because it's in a positive direction. Okay. Everybody all right with that? Okay. In part 2, our initial position is 25. Our final position is 33. Okay. So our change in position is from 33 minus 25. Okay, so that'll be 8. Divided by our time, which goes from 1 hour to 2 1/4 hours. Okay, so 2 1/4 minus 1 is 1.25. Okay, so 8 divided by 1.25 should give us positive 6.4 kilometers per hour. Are you okay with how I did that? All right, and then our last one, okay, our final position is 27. Okay, so 27 minus our initial position, which was 33, okay, and that takes another 1 1/4 hours because it goes from 2 1/4 to 3 1/2. Okay, the difference is on this one, I have 27 minus 33, which is going to give me negative 6. Okay, so I'm actually getting a negative displacement, which is fine because the object is clearly moving backwards in this section. The position is changing in a negative way here. Okay, we're 1.25, and that should give us our negative 4.8 kilometers per hour. Right? Now to do this over the whole trip, well, over the whole trip, my final position is 27. My initial position is 0, and it takes 3.5 hours. Okay, so I'm going to have 27 over 3.5, okay, and that'll give me my 7.7 kilometers per hour in a positive direction. Okay, everybody all right with that one? Make sense? All right. Don't want to go back to velocity versus time graphs just yet. So. No, there was one. It was question number 5. And where are my position time graph was? Okay, I thought I had more of those. All right, let's talk about what's going to happen here over the next couple of days. Okay, so imagining it is not a velocity versus time graph, but a position versus time graph. Okay, I want the total displacement and the average speed over the whole trip. Okay. All right, so on this one here, okay, we've got to find our total displacement. Okay, remembering that total displacement is final position minus initial position. So on this graph, our final position is 7 meters. Our initial position is 0. Okay, which means our total displacement is positive 7 meters. Okay, so that's the first part, finding the displacement. In order to find the speed, I need total distance and total time. Well, total time is easy, it's 15 seconds. Okay, just read that off the graph, but the distance is different. Okay, now I have to figure out how far does it go in each section of the graph. So in this first section of the graph, even though it went backwards, it still went somewhere, okay, it goes 3 meters. How far does it go here? 0, because it's flat. Then it goes from 3 to positive 7, so that's 10 meters, negative 3, sorry, to positive 7. So that's 10 meters. How far does it go here? 0. All right, so my total distance is 13 meters divided by 15 seconds. What was that, 0.86 or something like that? I shouldn't do stuff in my head. It's close. 0.87. Okay. Okay. 0.87. Actually, we only have one significant digit here, so it should be 0.9 meters per second. All right, we will leave it there for today. Okay, like I said, tomorrow, okay, we'll do a little bit of stuff on how Google Sheets works, which hopefully will be a review for everybody, and then we'll start looking at velocity versus time graphs.